Swayam Prabha. Digital India. Educated India.
So, broadly speaking, the problem is something like this. So, you have an unknown system, to which you have provided inputs, right? Inputs denoted in this sort of fashion, n inputs here. Next time you provide again another set of n inputs. And you have got some outputs. Okay. And what you would like to do is know what the system is like. And this is the sort of problem that results from this kind of formulation. Okay. Now, it is important here, if when you go about solving this problem, you can, it is important to that the matrix A is full column rank. Okay. And in particular, in it's in many one way that can be ensured is that you have if you are talking of a system and taking measure, and you have provided m different inputs, means you are taking measurements m times of the system. That means the number of measurements is greater than n, which is the length of the input or the number of parameters that you are trying to fit. Okay. In that case, this can be solved very easily. Okay. And has a non-trivial solution. Okay. Now, how is this related to what we have been talking about? The reason I brought this up is, if you look at this optimization problem, which is what the entire exercise of regression brought us down to, which is this optimization problem. What kind of optimization problem is this? This problem has a twice differentiable objective, right? And it is being optimized over the entire space of Rn. Now, the full space of Rn is obviously an open set. So, this is an optimization of a twice differentiable function over an open set. Now, because of the nature of the function here, it is just a simple quadratic function. This also admits a closed form solution, okay, using the pseudo inverse of A. But that's because of the choice of the norm that you have chosen. But in general, if you take some other type of loss function, you will not necessarily have a closed form solution. So, an example of this is one example of a optimization over an open set as an unconstrained optimization problem. Let me do another example of a similar flavor. In this case, we actually, here the problem is slightly different. Here the problem is that you actually have a model for the noise. Okay. So, suppose you have you have taken m measurements, and you have gotten these b the vector of measurements like this, b equal b1 till bm. These are m measurements that you have taken of a system, and we know that b should be equal to ax plus some epsilon, where epsilon is your measurement noise. Okay. So, what we do not know is x. So, you provided this inputs A, this is that is your matrix A here. Okay. You got these outputs or measurements B here, and we know that B and A are related in this sort of way. B is equal to Ax, but there is some measurement noise involved, which is epsilon. And suppose I am going to assume that we know that also that the noise has a Gaussian density. So, noise is distributed as a Gaussian random variable with mean as the 0 vector and covariance matrix sigma. Okay, so, this is the mean of the Gaussian random variable, the covariance matrix. So, when you get a string of these m measurements all corrupted by noise like this, but we know the density of the noise, we have we know that it has a Gaussian density. One philosophy for guessing what the x that resulted in these measurements is to say is to look at the likelihood. Likelihood is simply the density likelihood. Okay. Likelihood in this case is simply the density of the measurement, the probability density of the measurement. Okay. So, if these were discrete random variables, it would be the probability of seeing that particular measurement. Okay. And then say, okay, well, this is the probability of seeing this particular measurement with when when I gave these inputs. And then you ask, there is a hidden parameter or an unknown parameter here, which is x. You ask, okay, what parameter would have maximized the chance of seeing this particular measure? Okay. So, you look for the parameter x that maximizes the likelihood of seeing this particular parameter. Okay. So, you maximize effectively what you can say is the likelihood, find the x that maximizes the likelihood of the observed measurements. So, you find the likelihood of this. Now what would that be? That would be basically in this case, you are maximizing over x in Rn, the probability density evaluated at the measurements that you have received. This is the probability density of the measurement random variable evaluated at the observed measurements. Now, this is the probability density of this. So, this because well, the probability density, well, it is derived directly from the probability density of the noise itself, right, and the system model that you have built. So, consequently, it implicitly depends on x. Okay, so I will write a small x here just to denote that, just to indicate that there is a dependence on the x that. So, what we are doing is we are trying to say, okay, what kind of choice of x would have given me the highest likelihood of seeing this particular outcome. Okay. Now, there are criticisms about this particular philosophy of finding the x. That is a separate matter. That is not for our discussion. I want to get to the optimization problem that this implies. So, let's take this forward. So, this Px of B is actually nothing but can be written in the other in a different sort of way. Well, where I maximize over x in Rn, which is the probability of an epsilon getting realized, probability density of epsilon evaluated. So, this is now, let's denote this. So, this was probability density of B, this is the probability density of epsilon. So, this is probability density of epsilon evaluated at Ax minus B, right. So, what is the probability that epsilon turned out to give, you can say, take value Ax minus B. You are finding the x that gives me the largest such value. Okay. Now, it's quite convenient in this case to now instead of looking at the probability, you actually should, it's convenient to take the log of the probability, because log is a monotone function that does not affect the optimization. So, you can just simply, instead of doing a maximum likelihood, you do maximum log likelihood. So, do log of the probability of the density of the random variable epsilon evaluated at a x minus b. Okay. So, this is log of density of epsilon evaluated at a x minus b, and this so because this is a Gaussian random variable, this epsilon was, remember, in Rm, and this was a Gaussian random variable. The log of this, I can tell you, it's you get a, it has an expression, it's minus m by 2 times log of 2 pi the determinant of sigma raised to 1 by m minus half a x minus b transpose sigma inverse a x minus b, where, remember, sigma is the covariance matrix of the random. So, what we are doing effectively is doing a maximization of this function over x in Rn. Now, if you look at this function, you will notice that the first term here, the first term here has nothing to do with x at all. It is simply a constant. It does not affect the optimization problem. It only shifts the function laterally or in one direction. It has no bearing on the optimization. So, so as far as finding the optimal solution of the above problem is also the optimal solution of this problem, where you are, which is maximizing minus half a x transpose sigma inverse a x minus b transpose sigma inverse a x minus b. Okay, maximizing this second term. Now, that is maximization of a negative quantity, something that is negative. So, there is a minus sign outside, maximization of minus of this. So, that is what I can do is that is actually equivalent to doing a minimization of the same thing multiplied by minus 1. Minimization of this sigma inverse a x minus b. So, the x star that maximizes this quantity, the first optimization problem here is this optimization problem is the same as the x star that solves this particular thing. These are, you can get it is the same x star that solves this. The optimal value will differ because we have dropped additive constants that were there in the objective function. They have been dropped. So, they have to be added, they need to be adjusted for, but the x star is the same. The optimal solution is the same. All right. So, this is also another optimization problem over an open set. Okay. This is very similar to the problem of minimizing the norm of a x minus b, except that now the norm has been scaled with this sort of matrix in between, sigma inverse, right. So, it is or scaled, or rather the correct word is skewed by this matrix a x minus b, by this matrix sigma inverse. So, in general, all these problems tend to have this sort of form. They have the form of where you are minimizing the norm of some w times Ax minus b, the whole square, where w is your weighting matrix, is a matrix of weights. Okay, this is the general form of these problems. Okay, so this was another example of a problem that's can very commonly used in practice in many different disciplines. For example, power system state estimation. This is the standard model. Just so I wanted to demonstrate that as an application of optimization over open sets. Okay, now let us come to let's take this forward and let's see if there are problems other than problems that directly look like optimization problems over open sets, but will somehow get reduced to those. Okay, and this surprisingly is actually a very general class. So I will we can derive a very a general theorem about this, but that's not as revealing and as illuminating as doing an example. So what I will do is do an example, okay, and then I will state the general result. Okay, hopefully we can at least complete the example in today's class. So the problem is the following: you have, suppose you are in 2 dimensions, you have your x axis, you have your y axis. Okay, and suppose we have this thing here. Okay, this is a ellipse. Okay, it's given by this equation. Let me denote it by f1 of x comma y. This is given by x square divided by a square plus y square divided by b square equal to alpha, suppose. Okay, so any point on this ellipse, any x comma y that lies on the surface of this ellipse, okay, must satisfy this equation, and conversely any point that satisfies this equation, you can locate it on this ellipse. The problem for us is simply to find the rectangle with maximum area that can be inscribed in this ellipse. Okay, so how do you find such a rectangle? What I need to do is how do I define such a rectangle? Well, the rectangle can be defined in very easily. What we will do is we will make, for simplicity, we will make sure that the rectangle aligns with the coordinate axis that we have chosen. Okay, so because and that's possible. So what I mean by that is, suppose you take a point x comma y here. I will look at the corresponding point minus x, x comma minus y. Look at this point minus x comma y minus y, and this point which is minus x comma y. Take these 4 points and let's look for the rectangle of this sort of form that has the maximum area. Okay, so what is the area of this rectangle with these endpoints or these corner points? It will be 4x, right? It's 2x times 2y, right? So what we want to do is therefore find x and y such that you maximize the function 4xy, but then x and y should lie on the ellipse. Okay, so which means that x and y must solve this. Okay. Now, what does this mean? Now, what is the implication of this? So, if you look at this particular problem, you are maximizing a function that is differentiable, but then you are not maximizing it over an open set. You have to maximize this only over those points that are on the ellipse, that are on the locus of that of this function f1 of x comma y equal to alpha, right. So, so now if you look at the set of points that form this ellipse, this is actually a closed set. This is not an open set, and that then therefore becomes therefore a problem that is not in the previous category. However, what I will show you is that it is possible to still reduce it to something that we have seen before. Okay. So, let us